Students, continuation of circuit theory, that is network theory concepts. With respect to chapter 1, that is fundamentals of electrical circuits, I am discussing lecture 4. In the previous session that I given the detailed concept of resistance. That is, resistance is one of the passive element. Why the resistance in the conductors? What exactly linear resistance, non-linear resistance? What are the negative resistance characteristics of a resistor? All these points, and what are the formulas with respect to resistor, and different models of questions with respect to resistor that I discussed. Before starting the one more passive element, that is inductor, how to remember this note points, friends, with respect to resistor. We know that a resistor is a dissipating element. A resistor is a dissipating element. It cannot store the energy. Cannot store the energy. It dissipates the power or energy in the form of heat. It dissipates the energy. Dissipate the energy or power in the form of heat. The form of heat. Told already, if this is the resistor, let the current passing through the resistor is I. This is R. How to write? The energy equal to I square RT. This is equal to V square by R into T. But this I or this V, students, these are the RMS values. If it is a AC current, how to take? These are the RMS values. For AC, these are taken as a RMS values. It dissipates the power or energy in the form of heat. That's why it is not a storage element. It is a dissipating element. And one more point to remember, students. We know that resistance is measured, the units of resistance is ohms. Then resistance is measured as in different ranges of resistances are available. We have to measure at 10 power minus 6. This is you have to measure is a micro ohm. You can also measure resistance as 10 power minus 3. This is very small resistance is measured micro and milli ohms. And we can also measure resistance is 10 cube. This is the kilo ohms. You can also measure the resistance is as a 10 power 6 multiplied. This is in terms of mega ohms. You can also measure resistance is 10 to the power of 9 ohms. This is measured as in giga ohms. In different ranges, we have to measure the resistance. No doubt at all, the units of resistance is ohms, but it is measured in micro or milli, kilo, mega or giga. You can also measure if very large resistances, you can also go on tera resistance, but maximum you have to take the giga, 10 to the power of 12, that is tera. If you take lower value 10 to the power of minus 12, that is pico. But generally in micro ohms is the small values we are measuring resistance values. Giga ohms is measured as a high values in resistance. Then final conclusion point with respect to resistor, students. Therefore, a resistor is a linear bilateral. It offers same resistance for both the direction of the current flow. Bilateral, time invariant. It's not a time variant. It's a time invariant. Linear bilateral time invariant passive element. What exactly passive element? What is the active elements? What are the linear elements? What are the bilateral elements? What are the time invariant? What are the time variant elements? What is the passive? What is the unilateral elements? What is the lumped elements? What are the distributive elements? All these later on in the discussion of elements I will discuss. But up to now, you remember this is a final conclusion point with respect to resistor. A resistor is a linear bilateral time invariant passive element. One more important element in circuits, that is inductor. No doubt at all, inductor is also one of the passive element, but it is not a pure. I'm talking about pure inductor. Pure inductor is energy storage element, which stores the energy in the form of magnetic field. But practical inductor, every practical inductor is having some resistance. That's why practically, because of the resistance of the inductor, it dissipates. But general inductor means you have to take the pure inductor, then it is a storage element, it is not a dissipating element. If it is mentioned that practical inductor, every practical inductor is having some resistance, then it dissipates the energy. The inductor is a passive component which stores the energy, that is electrical energy, in the magnetic field. Very important. In which form it stores the energy? In the form of magnetic field. When the electric current passes through it, or we can say that the inductor is an electrical device, electrical element, which possesses the inductance property. Then what is the inductance property? The inductance is the property of a material. Students, I told already, resistor, resistance. Resistor is the physical element. Resistor is the physical element. Resistance is the property. Resistance is the property. Like that, inductor is the physical element. Inductance is the property. Inductance is the property. The inductance is the property of a material by virtue of which it opposes any change of magnitude and direction of electric current passing through the conductor. In other words, it is a property of coil in which the EMF is induced because of the variation of the flux. How the EMF is induced, all these letters. Okay, this what exactly inductor, and this is the inductor. We know that inductor store the energy in the form of magnetic field. That is, inductor store the energy in the form of magnetic field. This inductor storing the energy in the form of magnet. That means there is a concept of magnetic field. There is a concept of magnetic field. Magnetic field. We know that the magnitude of this magnetic field is given by how to determine the magnitude of this magnetic field, friends. Magnitude is determined. Magnitude is determined by using two laws. One is, can anybody, how to determine the magnitude of the magnetic field? The magnitude of the magnetic field is determined. One is a Biot-Savart's law. In detail about this, that you see in our EMF or EMPL subject, that is Biot-Savart's law. Is determined by using Biot-Savart's law. One more is we have to apply Ampere-Circuital law. Ampere-Circuital law. These two laws we have to apply to determine the magnitude of the magnetic field. We know that Ampere-Circuital law is applicable for only in closed path. Applicable only in closed path. Applicable only in closed path. That you have to remember. Now, what is this magnetic field? Students, we know that, let's assume that this is the conductor. I'm taking the straight conductor. Let's consider any one straight conductor. How to take any one straight conductor, students. Let this is the straight conductor. If this conductor is carrying the current, if any conductor is carrying the current, around the conductor, a magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are called flux lines. Those imaginary lines are called flux lines. Like this, flux is produced. If any conductor carries the, I'm taking the straight conductor. If any conductor carries the current, around the conductor, a magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are called flux lines. This is proved by Eisenstein experiment. If any conductor is carrying the current, around the conductor magnetic field is produced. This proof is given by Eisenstein experiment. All this is not required. Now the question is, how to determine this direction of the flux? The direction of flux is determined by using right hand thumb rule. By using right hand thumb rule, or you can also apply screw rules. That is, if any conductor carrying the current, if any conductor carrying the current, around the conductor, magnetic field is produced. Magnetic field is produced. Field is produced. It is represented by imaginary lines. Imaginary lines. It is called flux lines. It is called flux lines. Okay, that is the flux lines. The direction of flux is determined by using right hand thumb. The direction of flux is determined by using right hand thumb rule. By using right hand thumb rule, or you can also apply screw rule. Right hand thumb. Now, this right hand thumb rule we can apply in two methods, in two ways. If it is a straight conductor, thumb indicate the current direction, curved fingers indicate the flux direction. That is the magnetic field direction. Thumb indicate the current direction. Now apply this right hand thumb rule here. This indicate the current direction. The curved fingers indicate the flux direction, magnetic field direction. This is which direction, friends? Clockwise or anti-clockwise? This is the anti-clockwise. Apply right hand thumb rule here. Take the right hand figure. So you have to take the right hand. Then apply thumb is in the direction of the current. Thumb is in the direction of the current. In the direction of the current. Then these curved fingers indicate the magnetic field direction. This is a counterclockwise direction. The flux direction is counterclockwise. That is, this is for straight conductor. This is for straight conductors. If it is a straight conductor, thumb indicate the current direction, curved fingers indicate the magnetic field. If it is a coil, for a solenoid coil, or if it is a coil switch. If it is a coil, then thumb indicate these curved fingers are there. Curved fingers indicate the current direction, like this. The curved fingers indicate the current direction. Then thumb indicate the flux direction, that is the magnetic field direction. This is the north pole and this is the south. The flux lines are, this is flux direction means where the flux lines are starting. The magnetic field starting at north pole, that's where it is the north pole, and where it is entering, at south pole it is entering. This is south. If it is a coil, say for example, if the coil is like this. If it is a coil, if it is a coil, let the current direction is made like this. This is the current direction. This is the coil. And if the current direction is given like this, the current direction is given like this. Then if you apply the right hand thumb rule, friends, take the right hand, apply the thumb rule. Then this curved fingers indicates current direction, thumb indicates flux direction. The flux line, this is the thumb indication. The flux lines are starting here. Like this it is going. This is entering. Wherever it is starting, this is the north pole and this is the south pole. Like this, the flux lines are moving. You have to apply, friends. Along the direction, this different. I applied. Here you take the right hand, then apply the curved fingers along the current direction. Curved fingers along the current direction. This is the current direction. Then you can get, this is the thumb indication. This direction thumb is showing. Then these flux lines are starting here. Then this is the north pole. This is the south. Clear. Like this flux is produced. Then because of flux, once you know the flux, now you have to calculate what is the inductance, friends. Then how to calculate the inductance. Why I'm explaining all these minimum fundamentals concept? I told already. Inductance store the energy in the form of magnetic field. Then to get the formula for inductance, we can start from the magnetic field concept. Yes. Let's consider this is the coil. This is the coil. On this coil, we are placing some copper wire. This is the winding. This is the number of turns we are placing on the. Take any one core. On the core, you can place the wire. It becomes a one coil. It becomes a one coil. This is the direction of the current. If the current direction is like this, if you take, then apply right hand thumb rule. Then this is the flux direction. The flux lines are moving like this. This is the flux direction. Then this is the north pole. This is the south. Let the current is I. Let N equal to number of turns in a coil. Number of turns in a coil. Number of turns in a coil. One turn is nothing but a combination of two conductors. This is called one turn. This is called one turn. This is called turn. Let N equal number of turns in a coil. I equal to current through the coil. Current through coil. Current through the coil. Then how to define MMF? How to define MMF? That is a magnetomotive force. Number of turns into current is nothing but a MMF. This is in ampere turns. This is in ampere turns. The units of MMF is ampere turns. Then how to define the flux? How to define flux? Flux pi equal to MMF by pi equal to MMF by reluctance. Flux equal to MMF by reluctance. That is magnetomotive force by reluctance. Then how to write MMF equal to Ni. What the reluctance, friends? This reluctance equal to L by mu A. Reluctance equal to L by this reluctance equal to L by mu A. What is L here? That is the length of the air gap. L equal to length of air gap. Air gap, within the air gap, the flux is flowing. Length of air gap. Then you have to take A is the area of the core or magnetic core. Area of core. We have, what is mu here, friends? Mu equal to permeability. Mu equal to permeability. Permeability. How to equate mu equal to mu naught into mu r. Mu naught into mu. What is mu naught? That is absolute permeability or permeability of free space. This is the permeability of free space. Permeability of free space. Then what is this value, friends? 4 pi into, very important. many subjects, this value will useful. That is 4 pi into 10 to the power of minus 7 Henry per meter. The absolute permeability or permeability of free space, absolute permeability or permeability of free space is equal to 4 pi into 10 to the power of minus 7. 4 pi into 10 to the power of minus 7 Henry per meter. What is mu r? Relative permeability. Relative permeability. Mu r is relative permeability. Then if it is air core coils, for air, if it is air core coils, the air core coils are like this. For air core coils, what is mu r equal to, friends? Instead of iron, instead of using any core material, if you use the inductance like this without any core material, then these are treated as air core coils. Air core coils. I'm asking one question, friends. Is it air core coils are having high reluctance? Iron core coils are having high reluctance. Air core is high reluctance. Air offers the high reluctance. Reluctance is the property which opposes the flow of the flux, just like a resistance, which opposes the flow of the flux. For air core coils, mu r equal to 1. If you use the iron core coils, friends, for iron core coils, whose value mu r is greater than 100. The value of mu r equal to greater than 100. Yeah, this points many. That means if any magnetic material is having the high permeability, it offers the low reluctance and can easily allows the flux lines. That is, if any magnetic material, having high permeability, having high permeability, then it offers low reluctance, and can easily allow the flux lines, That is the property required for any magnetic material. Always the magnetic material must have high permeability to easily allow the flux lines. Even if the permeability is high, reluctance is less, to produce the required flux, the excitation is also less. Less excitation current is enough to produce the rated flux. This is the easily allow the flux lines. It is flux. What are the units of flux, friends? The units of flux is Webers. The units of flux is in Weber. Then once you know the flux, now you have to calculate the inductance, friends. Then before calculating the inductance, how to define the flux density? Can anybody? How to define flux density, friends? The flux density B equal to flux per unit area. The flux density equal to pi by A. Then what is the units of flux density? The units of flux density is Weber per meter square. That is Weber per meter square. Previous slide. Okay. Any doubt? Oh, thank you. Yes. Units are Weber per meter square, or 1 Weber per meter square equal to Tesla. 1 Weber per meter square equal to Tesla. That is B equal to pi by A. Then what is pi equal to B dot A? Yeah, this is the formula for flux. Once you know the flux density, you have to relate the flux density and magnetic field intensity or magnetic force. Then what is the relation between flux density and magnetic field intensity? We know that B equal to mu H. We can also write B equal to mu naught mu R into H. This one more relation. Is B equal to mu H, that equal to mu naught mu R into H, where H equal to magnetic field intensity, or magnetic force, magnetic field intensity or magnetic force. Now you have to define what is the flux linkage. How to define flux linkage? The flux linkage psi equal to n pi. Number of turns into flux, that is nothing but a flux linkage. Then psi is proportional to, how to define psi is proportional to pi. From this, what is psi? Psi is proportional to flux. The flux linkage is proportional to the number of flux lines. But what is flux equals, friends? Ni by L by mu A. This formula already you know. MMF by reluctance. Then what is the flux? Flux is proportional to current. Flux is proportional to current. That is, if psi is proportional to pi, psi is proportional to pi, then pi is proportional to I. Pi is proportional to I. See this one. You know the psi is proportional to pi, but this pi is proportional to I. From these two, how we can write psi is proportional to I. Then if you remove the proportionality, we can get one constant psi equal to Li. So just like V equal to IR, V equal to IR. Here we are getting psi equal to Li, where L is the inductance or self-inductance. Where L is inductance or self-inductance of coil. This is one of the property of the coil. Self-inductance of coil. Inductance or self-inductance of coil. And from this, psi is proportional to I, psi equal to Li. If you remove the proportionality, we are taking one constant, that is nothing but a S. That is, the flux linkage is proportional to the current flowing through the coil. Just like V is proportional to I, the voltage is proportional to the current, or the current is proportional to the voltage. Here, the flux linkage is proportional to current flowing through the coil. Then from this, what is the inductance L equal to? Inductance L equal to psi by I. Psi by I squares. This is psi equal to n pi by I. This is one formula. Remember, very important relations. The inductance L equal to psi by I, that equal to n pi by I. That equal to n pi by I. We can also write one more formula. Yeah, this one important relation to solve the problems. We can also write, just a minute, I'm adding the slide. Yes. Then inductance L equal to, how to write? The inductance L equal to that is n pi by I squares. N pi by. But what the flux equal to? Is n by I into, how to substitute flux? N by I into flux equal to MMF by reluctance now. That is Ni by L by mu A. This flux formula I am substituting here. This I cancel. That is N square by L by mu A. N square by L by mu A. L by mu A. Then N square mu A by L. Very, very important observation. Therefore, the inductance L equal to N square mu A by, this is equal to N square mu naught mu R A by, where N equal to number of turns. N equal to number of turns. This is equal to the inductance L equal to this inductance or self-inductance of a coil. This is the inductance. Then what is the observation here, friends? This is during design. The inductance is proportional to N square. The inductance is proportional to area of the core or coil. The inductance is inversely proportional to the length of the area. L is proportional to N square. L is proportional to A. Then L is proportional to 1 by H. L is proportional to, right? Yes. Then if you know this characteristics, psi equal to, if you remove the proportionality, we are getting, that is what the psi is proportional to Li, psi equal to Li squares. Then if you draw the characteristics, psi versus I, if you draw the characteristics, psi versus I, if you draw the characteristics, psi versus I, then this characteristics psi versus I, that this is psi and this is I, then we can get the linear characteristics. That's why inductance is a linear element. It's a linear characteristics. Then the slope of this curve, slope equal to, the slope of this curve indicate the inductance. This is equal to psi by A. What do you mean by linear characteristics, friends? What do you mean by linear characteristics? If I is increased by 20%, for example, if the current is increased by 20%, then what about the psi also? Psi also increased by 20%. Then we can say that this is the linear. This is the linear. For example, if it is a non-linear, for non-linear, what do you mean by non-linear? If I is increased by If I is increased by 20%, then what about the psi? Psi is increased by 10%. There is no proportional increase. There is no proportional increase. If I is increased by 20%, then psi is increased by 10%, then L depends on I and psi. Then L depends on, L is not constant here. L is not constant. Then L depends on psi and I, then L is not equal to constant. If L is not equal to constant, then it is a non. Even in the resistor also I told, when the particular resistor is said to be non-linear resistor. Non-linear resistor means the resistance is not constant. But here, L equal to psi by, this slope is constant. So slope is constant. If slope is constant at every point, L is also constant. Then we can say that it is a linear. This is for linear, this is for non-linear characteristics. If there is no proportional increment, if I is increased by 20%, psi is increased by 20%, then we can say that this is the linear. If I is increased by 20%, but psi is increased by 10%, then L depends on the I and psi. That's the reason why we can say that it is a non-linear. It is a non-linear. Okay, this is about psi equal to Li formula also you have to remember. This is the one formula during solving of the problems also. Now you have to write what is the formula for voltage across the inductor source. Let's consider this is the inductor. This is the inductor. And before that, what is the units of inductance? The inductance is measured in Henry. Units of inductance. Better to write here. The units of inductance is Henry. Inductance is. This is measured in terms of Henry. Measured in terms of Henry. These are units of inductance. Now we have to calculate what is the voltage across the inductor. The voltage across the inductor is nothing but we are calculating voltage drop across the inductor. Voltage drop across inductor. Voltage across inductor is nothing but voltage drop across the inductor. Voltage drop across the inductor. That this is the inductance, inductor, coil representation. Let the current through the inductor is I, the inductance is L. Let the voltage across the inductor is V. You have to write the voltage across the inductor VL equal to L into di by dt. The voltage across the inductor equal to L into di by dt. This one formula you have to. We can also write VL equal to d by, this is VL equal to L into di by dt. VL equal to L into di by dt. Can also write d by dt of Li. What is Li, friends? Psi equal to Li. This is also equal to d psi by dt. The voltage across the inductor is also equal to d psi by dt. Once you know the voltage across the inductor, then how to calculate current through the inductor? How to calculate current through the inductor? Very important observations. The current through the inductor equal to current through the inductor. So have to write the inductor. Once you know the voltage across the inductor, I am calculating current through the inductor. Then VL equal to L into di by dt. From this, di equal to VL by L into dt. To get the current, integrate both sides. Integral di equal to, that is 1 by L into integral VL into dt. How to take minus infinity to t. Why you are taking this minus infinity? Because it is an energy storage element. If it is energy storage element, let's assume that already there is some initial current in the inductor. Then if you integrate this, how you can write, friends? This I equal to, I am writing like this, 1 by L, this 1 by L, integral minus infinity to 0, V dt or VL dt, that is the voltage across the inductor, plus 1 by L, integral 0 to t, VL dt. Then what this indicates, this current I equal to, this is the initial current in the inductor. If initial current in the inductor is not given, you have to take this equation. IL of 0 into 1 by L integral 0 to t VL dt. This is also very important for this. If initial current in the inductor is given, you have to take this one, where IL of 0 equal to initial current in the inductor. Initial current in inductor. The initial current in the inductor equal to IL of 0. If initial current in the inductor is 0, then you have to write what is the voltage across the inductor. If initial current in inductor is 0, initial current in inductor is 0. Inductor is 0. If initial current in the inductor is 0, then how you can write current through the inductor? I equal to, how to write current through the inductor equal to, initial current in the inductor is 0 plus integral 0 to t VL 1 by L dt. This is equal to 1 by L integral 0 to t VL dt. Let if it is VL equal to V, simply write 1 by L integral 0 to t V dt. If voltage across the inductor equal to V, then you have to write this. This is the expression for current through the inductor. How to write the expression for current through the inductor and how to write the expression for voltage across the. But here, how to give very important observation during solving of the problems. These observations are. See, for example, this is a note 1. During solving of the problem, based on these models, based on this observation, already questions are there in GATE and ES6. For example, we know that voltage across inductor equal to voltage across inductor equal to VL equal to L into di by dt. Voltage across inductor equal to L into di by dt. If current is parabola, if different current shapes are given, if current is parabola, then what is the voltage, friends? Then what is the voltage waveform? What type of waveform we can get? L into d by dt of current is parabola. Na? What is the differentiation of parabola we can get? What is the differentiation of parabola we can get? Can anybody? What is the differentiation of parabola we can get the ramp. That means if current is excitation, if it is a parabola, then you have to take the voltage is ramp signal. If current is ramp, then can anybody tell what is the voltage across the inductor? L into d by dt of differentiation of ramp. What the differentiation of ramp will use? Step function. Differentiation of ramp will use the step function. If current is step, then what is the voltage across the inductor waveform? Voltage across the inductor waveform. Differentiation of step, what it gives? Impulse. Differentiation of step gives the impulse. For example, if current is triangular wave, if current is triangular wave, what is the voltage across the inductor space? L into d by dt of triangular wave. Then differentiation of triangular is square wave. Differentiation of triangular wave is square. If current is sine wave, what is the voltage across the inductor? If current is sine wave, what is the voltage across the inductor? Which waveform, sir? It is a cosine wave. Differentiation of sine will use the cos. Like this you have to write it. Sometimes it will give exactly opposite. If you write exactly opposite, note 2 I am writing. What is the current through the inductor, friends? What is the formula for current through inductor? The current through inductor, I equal to 1 by L integral V dt or VL dt. How to write? V dt or 1 by L integral VL dt. Now, if voltage is impulse, then what are the currents, friends? 1 by L integral differentiation of impulse. Sorry, integration of impulse. What integration of impulse will use? Differentiation of step gives impulse, means integration of impulse gives step. Reverse process. This gives the step. If voltage is step, then what the current? 1 by L integration of step. What integration of step gives? Ramp. Differentiation of ramp is step. Then integration of step is ramp. If voltage is ramp, then what are the currents, friends? The current I equal to 1 by L integral ramp. Integrating, we can get parabola. Differentiation of parabola ramp, integration of ramp is. Then if voltage is square wave, friends, square. If voltage is square wave, then what is the current we can get? 1 by L is a square wave. No? Differentiation of square wave gives triangular wave. So integration of square wave, not differentiation, sorry. Integration of square wave gives triangular wave. Differentiation of triangular wave gives square. Like this, during solving of the problems, this observation. This exactly reverse. This is differentiation. If you integrate this, we can get this one. This is differentiation of this. You integrate this, we can get. Integrate this, we can get this. Integrate this, we can get. If you integrate this, you can get this. Exactly. Students, we know that inductor is a energy storage element. It stores energy in the form of magnetic field. Stored energy in the form of magnetic field. But one observation you have to remember. See, for example, note I'm giving one more note. This is inductance. The current is entering. This is I. This is plus. This is minus. Then in this case, L storing the energy. L storing the energy. L storing the energy. If current is flowing like this is the inductor. This is the inductance. If current direction is like this, if the current direction is like this is plus, this is minus, this is plus, then current is leaving at positive, then you can say that L releasing the energy. L releasing the energy. L releasing the energy. And one more point to remember, L storing the energy, na? VL equal to L into di by dt. If L storing the energy, di by dt is positive. The slope is positive. The rate of change of current is positive. If L releasing the energy, this is the positive slope, friends. This is the positive slope. If L releasing the energy, what is the di by dt? Is VL equal to L into di by dt. Then di by dt is negative. That is falling slope. Releasing the energy is a falling slope. Storing the energy, rising slope. All these observations important. This is one direction. This is opposite direction. L releasing direction. But one point you have to remember here, friends. The property of inductor is like this. See, for example, initially inductor stores the energy. If the current is like this is very important. There is a main difference is there in inductor and capacitor in storing and releasing. Like this is the current direction. This is plus, this is minus. Then we can say that it is a storing. Then once inductor is completely store the energy, the property of inductor is it forcibly reverses its polarity. This becomes negative, this becomes positive. It reverses its polarity after complete storing. After complete storing, or if source is disconnected, reversing polarity. After reversing the polarity, then release the energy. After reversing the polarity, then release the energy. This is a property, steps. Then release the energy. Releasing the energy. This is happening. That is the property of inductor is once it completely stores the energy, our source is disconnected. The property of inductor is once it completely stores the energy, once it completely stores the energy, or excitation is disconnected, or if excitation is disconnected, inductor forcibly reverses its polarity. Inductor reverse its polarity. Very important observation, sir. During releasing, first reverse the polarity, then release the energy. During releasing the energy, first reverse the polarity, then release the energy. But capacitor is not like that. If you take capacitor, later on also I will explain. Let's assume that this is plus, this is minus. Let the capacitor is plus minus, it is a storing. Like this, it is storing the energy. Then, how to reverse the polarity? In capacitor, this is storing. Then capacitor release the energy. Second step is release the energy. Directly is not reverses polarity. Then capacitor release the energy. Let it is releasing the energy. Let assume that if the capacitor is, what do you mean by capacitor releasing the energy? Transfer of the charge from positive plate to negative plate. Then release the energy. This is release the energy. Second step is release the energy. Release the energy means transfer of charge from positive plate to negative plate. Once it is transferred, then it becomes negative, this becomes positive, then reverse the polarity. Sir, why this difference? The reason is it stores the energy in the form of electric field, it stores the energy in the form of magnetic field. This is the property of magnetic field. This is the property of electric field. Here, reverse the polarity, release the energy. Release the energy, then reverse the polarity. Then reverse the these two observations also you have to. That's why in releasing and reversing the polarity, there is a difference in the inductor and here releasing the energy means what is the meaning? Transfer of energy from positive plate to negative. Then negative plate becomes positive, positive plate becomes negative. Transfer of energy from positive plate to negative plate. Positive plate to negative plate. Next. And one more observation. Slide I'm adding. Sorry. Just 10 minutes. I'm adding the slides. One more observation that you have to concentrate. Students, we know that V equal to L into di by dt. That is V equal to voltage across the inductor. But the observation here, friends, at t equal to 0, at t equal to 0 means initially. T equal to 0 means starting, initially. If substitute t equal to 0, then what is the voltage across the inductor? Infinity. Voltage is infinity means open circuit or short circuit, friends. Voltage across the inductor is infinity. Voltage infinity means open circuit or short circuit? Open circuit. At t equal to 0, inductor acts as a open circuit. Open circuit means is current is exist? No. There is no current. That is initially, suddenly there is no current to the inductor. That's the reason why inductor cannot allow the sudden change of currents. Inductor, why voltage infinity means current is 0. At t equal to 0, I'm explaining. Inductor cannot, in detail about this, later on we'll see in the transient also, but up to now you remember this is a property of inductor. Inductor cannot allow the sudden change of currents. Sudden change of currents. Inductor cannot allow the sudden change of current because initially inductor acts as, therefore, initially inductor acts as an open circuit. Inductor acts as a open circuit. Inductor acts as a open circuit. Next, at t equal to infinity, t equal to infinity means final steady state, finally. Substitute t equal to infinity here. What the voltage across the inductor? Voltage across the inductor 0 means open circuit or short circuit? Short circuit. Voltage 0 means short circuit. Voltage 0 means short circuit. Therefore, finally, inductor acts as a short circuit. Finally, inductor acts as a short circuit. That is at steady state condition. Finally, inductor acts as a short circuit. Acts as a short circuit. That is at steady state. Inductor acts as a short circuit. Then we know that V equal to L into di by dt. V equal to L into di by dt. From this, what is all these are the observations? V by di by dt. Then what are the units? The units I told already. One more unit I am giving. This dt goes to numerator. This dt goes to numerator. That is volt to dash second by amperes. Volt to dash second per amperes. The dt goes to numerator. That is volt dash second per ampere. Or another unit is Henry. This is the units of inductors. The units of inductance. And we know that inductors store the energy in the form of magnetic field. How to calculate stored energy? The fourth observation is stored energy in inductor. This is very important formula that I'm going to calculate. Stored energy in inductor. This is very important. 5-star gunshot formula. How to calculate the stored energy in inductor? We know that inductor stores the energy in the form of magnetic field. Inductor stores the energy. Store the energy in the form of magnetic field. Form of magnetic field. Okay, this is also very important points. Don't forget this. Initially, inductor acts as an open circuit. Finally, it acts as a short circuit. Because of initially it is an open circuit, it cannot allow the sudden change of store the energy in the form of magnetic field. Then, in order to calculate what is the energy stored by the inductor, first I am calculating the instantaneous power. Instantaneous power. Then, how to calculate the Instantaneous power, students. The instantaneous power P equal to V into I. What is V? L into di by dt. That is L into di by dt. This is into I. Yeah, this is the instantaneous power that equal to Li into di by dt. Li into di by dt. Yeah, this is the instantaneous power. Once you know the instantaneous power, how to get the energy? Then what is the energy stored by inductor? Energy stored by inductor. The energy stored by inductor equal to E equal to RW. Any notation you have to use. Integral P dt. Here you have to use either capital letters or small letters. No problem. I'm following the capital letters. Then you have to use, that is a L into di by dt into I. That is L into Li into di by dt. Li into di by dt. Then I'm calculating energy stored by inductor. The energy stored by inductor here W equal to integral Li into di by dt into dt. This dt cancel. Then what the energy stored by inductor? The energy stored by inductor equal to L is constant, I into di. You integrate I with respect to di, students. Integrate I with respect to di. What you can get, students? I square by 2, sir. I square by 2. Therefore, what is the energy stored by inductor? The energy stored by inductor. The energy stored by inductor E equal to half Li square. Half Li square. So this is the energy stored by I. Very important 5-star gunshot far. This is a calculation of how much energy is stored by the that is the answer, right? Yes, but you can also write this formula. What is psi equal to Li? Psi equal to Li. Shall I write I equal to psi by L? Where psi is the flux linkage, friends. Then energy stored by inductor, one more formula is half into L. I am writing psi by L. Psi by L whole square. Then what you can get, friends? Psi square by 2L. That is one more formula for energy stored by the inductor. Psi equal to Li. That I am writing I equal to psi by L. The psi square by L square. LL cancel. Then we are getting the psi square by 2L. These are the different concepts of inductance or inductor.
Sure.
Any doubt? Is it clear, sir? If you have any doubt, please raise the question, then I'll reply. Any doubts, friends? It's okay? Yes. Then what are the practical examples of inductor, students? What are the practical examples of inductor? Just like resistors, I told already what are the practical examples of resistors? Like heater, iron box, incandescent lamp. Like there's so many examples I give. Mission field windings. There's so many examples I give. Like that, what are the practical examples of inductor? The practical examples of inductor is one is choke coil. Choke coil is one of the example for inductor. It is having the inductive nature. Even transformer is also having the inductance, inductive nature. Transformer windings, transformer. And AC mission windings also inductive nature. It is also having resistance, no doubt at all, but it is also having AC mission windings also having it. Even you take some passive filters also having the inductive nature. Passive filters. All these are the practical examples of the which having the inductive nature. We know that L filter, C filter. No? What is the purpose of using L filter? What is the purpose of using L filter? To reduce ripple in load current. So this is one of the inductor filter. Inductor filter is having inductive nature to reduce ripple in load current. To reduce ripple in load current. Reduce ripple in load current. We are using inductor filter. But point to remember, friends, practical inductor having resistance and capacitance also. Resistance and capacitance also. Resistance and capacitance also. No doubt at all. Any practical inductor you have to take. This is inductor. Practical inductor is represented with, along with inductor, there is some resistance, series resistance. How to use resistance. Then practical inductor is having some inductance and it is also having the resistance. Then what is the time constant? The time constant equal to L by R. The time constant equal to, in detail about this in the explanation of transient concepts, the analysis of RL circuit, RC circuit, RLC circuit, in DC analysis and AC analysis, later on I will explain. But this one formula you have to remember. This is the time constant. But you have a doubt here, sir. Resistance, okay. But how the inductors are having the capacitance? Students, we know that inductor is nothing but a, you take one core, on the core, we can place one term. Again, on this term, we have to place some insulation. On the term, we have to place the one insulation. Again, we place the one more term. Like this, we can manufacture. Like this, we can construct the inductor. That means in inductor, this is one term, this is another term. In between, there is an insulation. This is one conductor, this is one conductor. In between, there is an insulation. Two conductors are separated by some dielectric material. It acts as a capacitance. That means that is called turn to turn capacitance. That is in capacitance, there in inductor, there exists a capacitance between turn to turn. Okay, this is called self-capacitance of coil or distribution capacitance of coil. Okay, that is called, actually it's negligible, no doubt at all. But practically, every coil is having some inductance, every coil is having some resistance and capacitance also. But actually that is negligible. Okay, if you take this is the coil, inductive coil, then this is called a turn-to-turn capacitance. In some exact analysis, you have to consider this turn-to-turn capacitance. So this is the seed. This is called distribution capacitance. This is called distribution capacitance or self-capacitance of coil or self-capacitance of coil. Every coil is having some capacitance. This is called distribution capacitance or self-capacitance of coil. Practically, this distribution capacitance or self-capacitance of coil, it is calculated, practically it is calculated by using Q meter, by using quality factor meter. The distribution capacitance or self-capacitance of coil is calculated by using you have to conduct an experiment using Q meter, then you have to calculate the self-inductance or, you have to calculate the distribution capacitance or self-capacitance of a coil. And one more point how to remember, students, one more important point. We know that if the core is like this, it is a solenoid coil. If the length of the coil, if the length of the core is L, that is the air gap length is the L. This is L. How take this is the coil. We know that how to write the inductance. L equal to N square mu A by L. This formula all of you know. N square mu A by S. But if the coils are like this, if this type of coil it is given, there is a coaxial shape. If it is a coaxial coil, that the coil is like this, it is given. Okay, this type of coil it is given. The shape of the coil is like this. This is the shape of the coil. It is also inductive coil. Okay, this is placed like this. Just a minute. Where am I? For this type of shape, how to consider the length of the coil? Can anybody? For this type of shape, how to consider the length of the coil? The length of the coil is equal to circumference. Is it correct? The length of the coil equal to circumference. In this case, inductance equal to L equal to N square mu A by L. But what is L here, friends? Where L equal to 2 pi. Now take the total circumference of the coil is nothing but a L equal to 2. Actually, in the explanation of resistance also, note for resistance, R equal to rho L by A. Rho L by A. If it is a circular or if it is a straight conductor, you have to take this form. If the resistor is this shape, this is called coaxial shape, just like coaxial cable. It's like this. If it is a resistor, I'm writing for resistance formula also. I think electrical students, you know this formula, but AC students, you don't know. In cables, you studied about this. This is the inner radius, and this is the outer radius. Inner radius and outer radius. Then for this case, how to calculate the resistance? This is capital R is the outer radius, small r is the inner radius. Then resistance equal to, in this case, the resistance equal to 1 by 2 pi L, ln of capital R by small. This formula also you have to remember. Here resistance is inversely proportional to length. Very important. Generally, resistance is directly proportional to length. Na? For this coaxial shape, it is given. Then resistance equal to, this is equal to 1 by 2 pi L ln of R by this resistance. This resistance is measured. Mainly in tables, you have to calculate the insulation resistance. Then you have to calculate this 1 by 2 pi into ln of R by R. Okay, this is about the detailed discussion of the inductance. The property of inductors are very important. Inductance cannot allow the sudden change of current. Initially, inductor acts as a open circuit. Finally, inductor acts as a short circuit. Finally, inductor acts as a short circuit. Then inductor cannot allow the sudden change. Inductor store the energy in the form of magnetic field. Inductor store the energy in the form of magnetic field. All these points you have to consider. Friends, any doubt up to now? I started. What is the inductor? Inductance that I given. Then final conclusion point that you have to write with respect to inductor. Then finally, the inductor is a also linear. Inductor is a linear. Therefore, the final conclusion point is, and final conclusion points, friends. Therefore, inductor is a linear. It is a linear element. Bilateral, both the direction it offers the same impedance. Bilateral, same reactance it offers. Bilateral, time invariant. It's not a time variant. Time invariant. Linear, bilateral, time invariant, passive is a passive element. Passive element. This is the linear, bilateral, time invariant, passive element. Passive element. This is the final conclusion point with respect to it. Here I'm giving one small question, friends. Can anybody answer? So, for example, a practical time constant for a practical inductor, for a practical inductor, for a practical inductor, for a practical inductor, if the number of turns in the coil is double, if the number of turns in the coil is double, if the number of turns in the coil is double, if number of turns in the coil is double, then its time constant is, what is its time constant? Then it's a time constant is, time constant is. Can anybody? Then its time constant is. How many times it becomes? The time constant is 2 times or 3 times or 4 times or remains same. Try this. Answer this. So I'm giving practice one. Tomorrow I will ask this question. Answer. For a practical inductor, if number of turns in the coil is double, the coils are double, turns in the coil is double, then it's time. If the number of turns in the coils are double, then it's a time constant. Friends, this is the about a detailed discussion of inductance. Then you have to start the capacitance. When I start this, it will not complete. Better to continue tomorrow. In tomorrow class, I will complete this capacitor concept. Then we have to see some practice questions with respect to inductor and capacitance. How to see some practice questions with respect to inductor and capacitor. All these practice questions that I will solve. Then with this elements, RLC elements will complete. That is the basic elements in the circuit theory. Resistor, inductor, and capacitor concepts will be complete. And after that, we will see the types of elements. Then KCL, KVL, model analysis. Students, any doubt? Okay, thank you. If you don't have any doubt, then I'm ending the session. I will share this PPT. Please go through this once again. Thank you.